So we will resume our formalism of quantum mechanics, but today let me start by comparing classical physics with quantum physics and write down what are the differences between the two and how you make a transition from one to the other. So let us go back and look at Hamiltonian mechanics, because the whole of quantum mechanics also presumes that you have a Hamiltonian for the system, and quantum mechanics is really concerned with Hamiltonian evolution in the presence of a Hamiltonian. So classically you start by defining dynamical variables. So this is classical and this is quantum. Okay. And these dynamical variables are of two kinds. There are q1, q2, etc., and then there are p1, p2, etc. So they go in pairs, as we see, complex conjugate pairs, canonically conjugate pairs, and then these dynamical variables satisfy Poisson bracket relations, and the Poisson bracket relations are qi pj equal to delta ij, and qi with qj is 0, pi with pj is 0, etc. So let us even write that down, qi with qj equal to pi with pj equal to 0. Okay. Now of course no dynamics has been put in so far, it just says you have set of variables and they obey these relationships among each other, these algebraic relationships. The dynamics comes in prescribing the time evolution equations, and it says, so you introduce a Hamiltonian which is a function of q and p, there exists a Hamiltonian which is a function of the dynamical variables such that qi dot is delta h over delta pi and pi dot is minus delta h over delta qi. This is the Hamiltonian formalism in classical mechanics. And what is the statement made? The statement is that in phase space, in the space of the q's and p's, specifying initial data corresponds to specifying a point in this phase space, after which you are supposed to solve these equations, and if this is an autonomous Hamiltonian, then the trajectory of the point that you started with in phase space will tell you what the future values of the dynamical variables are, and therefore you made you use this information together with initial conditions to find out what happens to dynamical variables as time evolves, as time elapses. Okay. Now the important thing to note here is that there are two pieces of information. One of them is this dynamical piece of information. This tells you what the equations of motion are, how things evolve in time. But this piece of algebraic information is input. It tells you a basic algebraic relation in this phase space between the q's and the p's, and it is not hard to see that these relations are valid at all times. In other words, at any instant of time, qi at time t with pj at time t is delta ij. If you start with that, it continues so. So the Poisson bracket relations themselves remain preserved as time goes along. The q's and p's adjust themselves such that they always obey the Poisson bracket relationship, which is why you could use any one of the points as the initial state, initial condition. Okay. So this is very important to understand. There are two sets of relations. One is the structure, the Poisson bracket structure, the canonical variables, and the other is the evolution equations. Okay. Now when you come to quantum mechanics, our assumption is going to be that you still have this, these things are replaced by self-adjoint operators acting on the vectors of some Hilbert space, let us presume. So I will put that in brackets, acting So just as you had phase space here, so this is dynamical variables in phase space, the phase space here is no longer here in this in the quantum version, is no longer a phase space because it is meaningless to talk about points in phase space due to the uncertainty principle, due to the quantum nature of these variables. That is replaced by the Hilbert space. Okay. So the appropriate space in which things happen in quantum mechanics is the Hilbert space of states. We have still got to say where a state fits into this, where state vectors fit into it, but the dynamical variables are replaced by self adjoint operators here. Then what about the Poisson bracket relations? Is there an analog of those relations here? If so, it must be a relationship between the operators, and the relationship that has been found to be the correct counterpart of the classical one is the Poisson bracket relations are replaced by PBs replaced by commutator brackets. Okay. And what is the commutator of two operators? It is the difference of operating with the two operators one after the other in different orders. So the commutator here would be Qi Pj. This stands, by the way, this is a shorthand for Qi Pj minus Qj Pr, a shorthand for that. If these are matrices, then it says you have two matrices A and B, the commutator is AB minus BA, that is also a matrix. If they are general operators, well, the operator Q followed by the operator P minus the operator minus the other way, Pj Qi in the opposite order. Okay. That is an operator too of some kind. So what happens in quantum mechanics is the Poisson brackets are simply replaced by the commutators divided by IH cross, need that factor there for a reason I will come to in a second, and this is equal to delta Ij, but then these are operators. So there must be an operator on the right hand side, and the appropriate operator here is the unit operator. It does not do anything, it just acts on a state and leaves it as it is. But the I and j are the component or the labels which specify the dynamical variables. They could be Cartesian components, they could be just the labels of the dynamical variables, the phase space variables in the classical case, or the canonical variables. So of course the other two commutators are 0, so Qi Qj equal to 0, Pi Pj equal to 0. These two are also part of the algebra. So some algebraic relationships between the operators replace the algebraic relationships for the canonical variables. The Poisson brackets are replaced by commutators. Why do I need that IH cross? The answer is technical. These quantities are physical quantities, they are real variables, they are real quantities here. The corresponding thing here would be self adjoint operators, but you see the the commutator of two self adjoint or Hermitian operators is not Hermitian itself. You can easily see this. Suppose you have a matrix A and it is Hermitian, and a matrix B which is Hermitian. They both would represent some physical operators, physical quantities. Then the commutator A comma B equal to C, say it is some other operator, call it C, then C is AB minus BA, but C dagger equal to, you have to take the dagger here, and when you take the Hermitian conjugate of the product of two matrices, it appears in the reverse order. So this is equal to B dagger A dagger minus A dagger B dagger, but that is equal to BA minus AB, because B and A are themselves Hermitian, but this is equal to minus C. So a commutator becomes anti-Hermitian. On the other hand, if it is a physical quantity, which is what it should be because A and B are both physical quantities, so just the combination AB minus BA is also an observable, then you must make it Hermitian. That is the reason why you need this I here, because the moment you put the I, that also changes sign and it makes this quantity a Hermitian quantity. Okay. The H cross for dimensional reasons, because you can see that the product of any generalized coordinate and any generalized momentum, corresponding conjugate momentum, has always got the dimensions of energy multiplied by time, and there is a fundamental quantum constant, Planck's constant, which has the same dimensions. So this makes it dimensionless here. You could ask, why not minus IH cross? Why not minus IH cross? This turns out to be the right prescription, plus IH cross turns out to be the right prescription, and we will see as we go along what would happen if you had a minus here. So the algebraic structure here goes to the algebraic structure there. The next question is, what about these equations? What do they look like? What kind of equations would you have? You again have a Hamiltonian. The presumption is you again have a Hamiltonian, which is a function of Q's and P's, except these are operators, and therefore the Hamiltonian is also an operator, and you can immediately see that if Q and P are complicated operators like derivatives and so on, and then you take functions of this derivative operators, you can get fairly complicated operators. Suppose P involves differentiation of the state vector, then this H would be some function of this derivative operator, perhaps e to the power d over dx and so on. So you need to be careful, because this thing can be quite complicated when you write this down, and it is some operator here. But then are there the analogues of these equations? And the answer is no. There are no direct analogues of these equations as it stand. The equations are going to be slightly more complicated, and we will see what these equations become. So let me put a question mark for this. So that replaces this, and then this thing here, question mark. What does that become? That is really where the whole thing is. I mean, what is the time evolution of a quantum system? How is it described, and so on. Now keeping this in mind, let us go back and look at what we said about expectation values, and then we are going to get a hint as to what is going to happen. I pointed out that if you took a physical observable and I ask what is the expectation value or average value of this observable at some instant of time in a quantum system specified by a certain state, then we ask the following question. The state of the system psi of t is given to you at some instant of time, and now I ask the following question. What is A at that instant of time? So perhaps I should put a bracket t there and so on, but at that instant of time, what is this quantity equal to? I explained yesterday that if you make a measurement on this system to measure this physical quantity A, you are guaranteed to get one of the eigenvalues of the system. Which one it is, you can't say a priori, depends on the state of the system. So now let us assume, for simplicity of notation, that A has eigenvalues lambda 1, lambda 2, etc., possibly an infinite number of them, possibly continuous and so on, we do not care at the moment. Just for notation, let us call them lambda sub I, and eigenvectors or eigenfunctions, eigenvectors phi 1, phi 2, etc. So suppose he has these guys, then I assume to start with that these eigenvectors form a basis set in this Hilbert space of the system. This is an assumption. There would be operators for which you may not be able to justify this, but just to set the formalism, let me tell you where, let me assume this, make this assumption here. It is a Hermitian operator or a self-adjoint operator. It has these eigenvalues and these eigenvectors. In other words, A acting on phi n is lambda n on phi n. Okay. And these form a basis. They form an orthonormal basis. That immediately implies that I can expand psi of t at any instant of time in the form summation over n, all the allowed values of n, some coefficient Cn times phi n. Now this operator A is perhaps like position, angular momentum, etc. It is supposed to be made up of the dynamical variables of the q's and p's, and there is no explicit time dependence in A. We assume to start with there is no explicit time dependence in A. After all, if I want to measure the position of a particle, that position x has no explicit time dependence. It may depend on time after you solve the equations of motion, but there is no explicit time dependence. On the other hand, I could also say let me measure x squared plus y squared plus t times z squared divided by some tau or something like that, some combination. So I could put in t explicitly, and then of course this variable, this function, this observable becomes explicitly dependent on t. But let us start by saying A is not explicitly, it is not explicitly time dependent, in which case it has some eigenvalues, it has some eigenvectors. These eigenvectors are found once and for all, they form a basis set, and I have an expansion of this kind here. If it is an orthonormal basis, this is a unique expansion here. Where is the t dependence go? They must go into the coefficient, it must go into the coefficients here of course, because imagine in 3 dimensions I fix my coordinate axes x, y, z, these are the unit vectors, and I take the position of a particle which is moving and I expand that in this basis, then of course the components are the ones that carry the time dependence, right. So you would say immediately that r of t equal to x of t times Ex plus y of t times Ey plus z of t times Ez. So it is these components and not the unit vectors that carry the time dependence. In exactly the same way these components carry the time dependence here. They would change from instant to instant, the basis is fixed to start with. Okay. Then once I do this, what is the expectation value? Well, what does this imply? This implies that the probability amplitude that the state psi of t is in fact the unit vector phi n is given by this here, and the probability interpretation of quantum mechanics says that mod psi n mod Cn of t whole squared is the probability that the system that is a postulate, that this probability amplitude modulus squared is the probability that the system is in a state phi n at time t. Now of course you may start with a state which is not normalized to unity. That presumes that the state is normalized to unity, because you immediately see that if I do a psi of t bra vector here, then by orthonormality we know this psi of t equal to summation over n mod Cn of t whole squared. That follows by orthonormality immediately, and therefore this is a probability provided this is unity, provided you say that the probability is 1, this is normalized to unity. But of course if I give you an arbitrary state, there is no reason why it should be normalized to unity, just as I can expand this position vector in terms of some vector along the x direction, something along the y, something along the z, may not be unity, may not be unit magnitude. Only if I make it unit magnitude can I talk about the magnitude of this vector as exactly equal to x squared plus y squared plus z squared square root. I have to first normalize these unit vectors. I may not do it all the time, I may start with an arbitrary state and I will not do it, and we need not normalize it. what would you then do? You do exactly what you do in statistical physics, you divide by the normalization factor, which in statistical mechanics was called the partition function, right, because the relative probability of a system having an energy E in contact with a heat bath at temperature beta, inverse temperature beta, was e to the minus beta E, but the absolute probability was e to the minus beta E divided by the sum over all these etas. So you have to keep track of that, of the normalization all the time. So provided equal to 1, provided you have normalized. If not, divide by the norm and then you normalize. This is how you normalize any vector. You take the vector, divide by its magnitude and you get a unit vector. So we will assume that we have normalized this state. We will see what happens if you do not normalize it as soon as we write the formula down. If that is the case, we can write a formula down for the average immediately. This immediately implies that A average is equal to the weighted average summed over n of all the eigenvalues of A together with the corresponding probability. When it is in the state phi n, the value of A is lambda n, you are guaranteed this is the value it would produce, and now you know the probability with which it is in the state phi n, it is mod Cn squared. So it is immediately clear that this quantity is mod Cn of t whole squared times lambda n. That is the meaning of the average. Once you give me a probability distribution, the average is just the value at each point in which the probability distribution fires multiplied by the probability. Incidentally, if this were not true and it were not normalized, what would this become? You would simply divide by n mod Cn of t whole squared. In general, this is what it would be. If you did not normalize it, you would just divide by the total probability, total sum, and that is it. But what does that tell you? So we have here a formula which says A, and it is a function of t. So in fact it is the average as a function of t, and I will explain why I am using this kind of strange notation a second, is equal to summation over n. The reason I am using this is because I have already said A does not have explicit time dependence. If I put A of t bracket inside, then you would think that A is a function of time. A is a dynamical variable, some observable, which does not have explicit time dependence. Its average value has time dependence because the state is changing from time to time, and there is the average in that state. So this is summation lambda n mod Cn of t whole squared divided by summation n mod Cn of t whole squared, but that can be written in a slightly different way. I would like to go back and write it in terms of psi to get a compact formula. So this is equal to summation over n lambda n, and what is Cn of t? Cn of t is this guy. So I take its complex conjugate, and what does that give you? Cn star equal to psi of t by n, because the complex conjugate of this is these two guys reversed, as we know. So let us put that in, and this says psi of t, this is Cn star that I am writing, phi n psi of t divided by summation over n psi of t phi n phi of t. Okay. I have just written down what is Cn star and Cn, mod Cn squared I have written as Cn star Cn, but then of course this thing here, the summation can be moved in. So you could move the summation in and write this as psi of t, because that has nothing to do with the summation. The summation over n lambda n yes phi n psi of t ket vector. Now you see the power of this notation, this is psi of t summation over n phi n psi of t. Now you see the power of this notation, this thing here is a number, this whole thing is a number, so it must have two angular brackets, a sharp point on the left, arrow on the left, arrow on the right, which is what it is. So what I have done is to move this out of the summation, because we know that the sum over n of these scalar products, you could take the sum inside and sum one by one because it is a linear vector space. So when I dot with a vector on the left, a sum of vectors, I can dot each one of them and add it up, or I can add the vectors up and then dot it, it does not matter. But what is this? This could be written as summation over n, what did I do? Oh, I erased the line I wanted actually. So this is equal to psi of t summation over n lambda n phi n psi of t divided by psi of t summation over n phi n psi of t. Okay. But what is this quantity? That is the unit operator. So in fact the denominator becomes equal to psi of t, which is the normalization factor as we expected. But what do you do with the numerator? I can't take this out and call it the unit operator, because the lambda n's are sitting there, the weight factors are sitting there, but we also know this, we also know that A acting on phi n equal to lambda n on phi n. So we use this relation in reverse, and this lambda n phi n, I write it as A acting on phi n, but A is a linear operator. So when it acts on a sum of states, it is as if you can sum those states first and then those vectors and act with A. So you can move this A out of the bracket. And now you could use the fact that this is a complete set of states. So what happens to this? This goes off and you get psi of t, and at the bottom, as we saw, and that is your A of t. This is a fundamental formula. So let us put A here and the psi of t. Does the numerator remind you of anything? You have this A sandwiched between two states, it looks like a diagonal matrix element in a basis in which psi is the basis, one of the basis vectors. This is what a matrix element means. This is the reason why in quantum mechanics we say matrix elements are expectation values. It is just matrix element in some weird basis of psi. But this is the basic formula, this thing here. Please notice this is how the A appears inside, in between these two guys here. It is by this little piece of rigmarole where you know that once you put in the probability interpretation, it follows that the expectation value of A, apart from that normalization constant below, is in fact the matrix element of A. Take the state vector psi, operate with A, you get a new state vector, take the inner product with the original state. that gives you the expectation value. Very important to notice that A is sitting inside, it is sitting inside. So there is no reason to expect that if you normalize psi, this is not normalized to 1 or anything like that. This is some very complicated object here. So the whole purpose of everything is to find these quantities, is to find these things here. You need to find what this number is in there. Now this gives us a hint as to what these equations of motion would look like. Whatever they are, whatever these equations of motion are, they should be such that when I take average values I recover this. In a sense this should be the solution to the problem. I should be able to recover that formula here, okay. So we will keep that in mind, keep this thing in mind. Now of course you could ask, what is dA over dt, how does this change as a function of time? Well, the time dependence is sitting here and here and here and here, and you have to put it in and see what happens, but you need now a rule for how psi of t changes. So I will start with that because there are two ways of doing quantum mechanics. At this stage there is an active way of doing it which follows directly from this, and it is called the Heisenberg picture, and there is another way of doing it which is called the Schrodinger picture, which specifies what the state vector does as a function of time, and these two are completely equivalent to each other because they will lead to exactly the same answer for these physical quantities, these measurable quantities. That is the consistency check. So without further ado, let me write the Schrodinger equation down here to show you how this thing changes as a function of time, how the state vector changes. So we replaced dynamical variables by operators, we replaced Poisson brackets by commutators. Next thing we do is we replace the phase space by the Hilbert space of the system. We replaced knowledge of the phase space variables by knowledge of the state of the system, state vector of the system. How do the phase space variables change with time classically? According to Hamilton's equations of motion. How does the state vector change as a function of time? According to Schrodinger's equation, and that is the input here, and the Schrodinger's equation is Schrodinger equation says IH cross, let me write it down, it is so important that that is a postulate. Go to get psi of t. Okay. That is the fundamental equation of quantum mechanics. So the way I have introduced it, I have put it in, I have said it is a postulate. What kind of equation is it? Is it an eigenvalue equation? No, no, it is not an eigenvalue equation, because this here tells you we have to define what this quantity is, but intuitively we know what it is. It is take the state vector at time t plus delta t, subtract the state vector at time t, divide by delta t, and you get some other vector. So IH d over dt on psi of t, some derivative operator acting on psi of t, is given by the action of the Hamiltonian on the state. So it takes you to some other state vector. After all, this is an operator, the whole point is this is an operator, and it takes you to some other state altogether. When we discuss eigenstates of this operator, then we will see that this equation reduces to an eigenvalue equation, but only for those eigenstates. In general it is a first order differential equation, but an operator equation for vectors in a Hilbert space, in an abstract space. So you got to be a little careful here about how you deal with these things, and you can't make much further progress unless you know what this Hamiltonian is and how to represent this Hamiltonian. That will be our task, to see how to represent this Hamiltonian and how to actually solve physical problems here. But this is not an eigenvalue equation as it stands. What is the order of the equation? It is first order in time. So in principle if you treat this like an ordinary differential equation, in principle this together with initial an initial condition is needed to solve this equation, to solve it uniquely. And what is that condition? The unknown here is the state vector psi of t. So you have to specify for me the state at some, you have to give for me the state at some initial instant of time. It is an initial value problem. So we will assume that we know the state at some instant of time, we will see later how we have to specify, how we can possibly specify these states, plus initial condition psi of 0. Is this an autonomous equation? Is it an autonomous? Yes, indeed it is, in the same sense that if this H does not have explicit time dependence, this is an autonomous system. Similarly, if this H is a function of just Q's and P's, then it is very much an autonomous system. There is no explicit time dependence here in this H, and if I change t to t plus delta, nothing happens, d over dt does not change. So it is clear that this whole thing is time translation invariant. You could choose any instant as the initial instant of time, just as you could for an autonomous system. What is the solution of this equation? What is the formal solution of this equation? Then comes the question of whether it exists, whether you can write it in this form or not. So for the moment think of psi, it helps to think of psi as a column vector in some space, some vector space. H you think of as a matrix in that space, square matrix acting on this column vector. What is the solution to this equation then? Exponentiation. So it says this implies that psi of t equal to e to the power h t over I h cross. So let us put the I upstairs, e to the minus I h t over h cross psi of 0. Formally, it is another matter that you may not be able to exponentiate it all the time, but formally this is true. Please notice that you need to have a state vector at time t, therefore that initial vector is put on the right hand side and this operator e to the minus I h t over h cross acts on it from the left. So ordering the order starts mattering here in quantum mechanics. Be very careful because things do not commute with each other. So whatever liberties you could take classically by taking a product of dynamical variables, putting them in any order, will not be correct in quantum mechanics. You have to worry about the order. One instant of that is that this sort of matrix equation, whatever, you need to put this on the left and the initial condition on the right here. Suppose I chose t0 as my initial instant of time, what would happen to this solution? Suppose I chose some arbitrary number t0 and I ask what happens in future, what would happen to this solution? Yeah, it just becomes t minus t0, nothing new happens, t minus t0 acting on psi of t0. This is a formal solution. Now we know that classical evolution here, this thing here, Hamiltonian evolution, preserves the volume in phase space. That was Liouville's theorem. That was one of the crucial inputs. The volume in phase space was preserved. So phase space flow in classical dynamics is like the flow of an incompressible fluid in real space. Is there an analog there, is the question. The analog would have to again do with the probabilistic evolution. So this is just like saying here that points do not disappear from phase space, this fluid moves around, this volume element does not change. In exactly the same way here too there is a conservation which operates, and what is that? The norm will be preserved, the norm of this vector will be preserved. So you can see that psi of t equal to, what is this equal to? In what order should these operate? the order is inverted. This is a matrix, that is a matrix, this is an n by n matrix, that is a column vector. So when you take the adjoint, it goes in the other direction. So this becomes psi of t0 e to the plus I h t minus t0 over h cross, but you must also conjugate that. The I becomes minus I, but the matrix H must become H dagger, and it acts on from the right. But is H Hermitian? Yes, it is. It is the Hamiltonian of a system. It is Hermitian. So all the systems we are going to look at, we are going to assume are described by Hermitian Hamiltonians. When you include dissipation in quantum mechanics, then you may need Hamiltonians which are not Hermitian. The reason is dissipation would mean the energy is not conserved, things would die down as a function of time, etc. But as long as the eigenvalues of the Hamiltonian are real, this can never happen. Damping would involve imaginary constants, imaginary components, and for the moment we look at systems with Hermitian Hamiltonians. So this goes away. That is it. Therefore, what is the norm? Therefore, what is this? What is this equal to? Well, one can close one's eyes and put this on the left and this on the right, and you have psi of t naught e to the I h t minus t naught over h cross e to the minus I h t minus t naught over h cross psi of t naught. What do I do next? I have e to the something, e to the minus that thing. How do I know? How do I know? How do I know this? These are all operators. I got to be very, very careful now. How do I know this? I have e to the a, e to the b. Is this true? If that were true, yeah, if a and b commute with each other, then it is true. If a and b do not commute with each other, then this is not true. In fact, there is a complicated formula, and we are going to use that formula over and over again. But of course this is true, e to the a, e to the minus a equal to a minus a equal to e to the 0. That is certainly true, because a and b commute with each other, a and minus a commute with each other. So please remember this is not true unless a commutator b is 0, and of course a commutes with any scalar multiple of itself, and therefore e to the a, e to the minus a is indeed 1, and this becomes a unit operator, and therefore this gives you a preservation of norm. That is the analog of the Liouville theorem, which says the volume element in phase space is preserved. Here the quantum evolution says the state vector preserves its norm as time goes along. That is a consequence of the fact that this operator here, its Hermitian conjugate is its inverse. It came out from that fact that the Hermitian conjugate of that operator was just the inverse of that operator. And what does that mean? We could regard this operator e to the power minus I h t minus t naught over h cross. This is an operator, let us call it something, let us call it an operator u t comma t naught. It depends on t and t naught, happens to depend on difference t minus t naught in this simple case, and this operator takes the state of a system from what it was at time t0 to what it is at time t. What should you call this operator? You call it the evolution operator, right, or the time development operator. When I take its matrix elements, I will call it the propagator, because that is what propagates you from one place to another, one time to another. Now this time development operator has some interesting properties as it stands. What is U dagger? I have to take Hermitian conjugate everywhere. So this becomes plus I and this becomes H dagger, and of course these are real numbers, nothing happens to them, but H dagger is the same as H, therefore U inverse. Or U dagger is 1, is the identity operator. I have just left out the time arguments just for convenience, but what do you call a matrix which has these properties? Unitary. So the time development operator is unitary. It satisfies some important properties, among which unitarity is first and foremost, the fact that it is unitary, but this leads to the conservation of the measure or the conservation of this quantity. Here if you identify this with the probability, total probability, then it says the conservation of probability follows from the unitarity of the time development operator. So unitarity is going to be put in. You find a time development operator which is not unitary, you know it is wrong immediately, you know that probability is not going to be conserved. So this unlike classical physics where Liouville's theorem did not seem to play much of a role, it just happened so that it was unitary evolution, I mean that it was volume preserving evolution, at least in elementary treatments it did not seem to play a very fundamental role. In quantum mechanics on the other hand, the unitarity of the evolution is very important, you have to keep track of that at all times. I will mention here that even if H is time dependent explicitly and the Hamiltonian changes from instant to instant while remaining Hermitian, the time development operator is not given by this formula no longer, it is not given by this. You can't do that because as you can see even in elementary differential equations, if this coefficient becomes a function of time, then this is not exponential, is not the solution, you need some e to the power some integral and so on. The time development operator in those cases would continue to be unitary, it would continue to be unitary, and we are going to look at some problems where it becomes explicitly time dependent. For instance, I take an atom and I switch an electric field on and off, then of course there is a time dependent Hamiltonian and I need to know what the time development is. Okay. This operator has the following property. In time, suppose this is the instant t0, this is the instant t1 and this is the instant t2, as time elapses this direction, then you could ask what is u of t2 comma t0 equal to, and it is immediately clear from this exponential structure that this is u of t2 t1 u of t1 t0 in that order, not in the reverse order, and the order is important. Of course here there is the Hamiltonian which is time independent, so it does not really matter, but in general once again you have to keep track of this. What does this say? This says that the system propagates from time t0 to time t2, the state evolves from time t0 to time t2. If there is an intermediate time t1, then this evolution operator which describes the evolution from t0 to t2 says goes from t0 to t1 first and then starts at t1 and goes to t2. in this order. You can't interchange these orders except in the simplest of cases, and this is called a semi-group property. You can see why it is called a semi-group sort of intuitively. You know, when you have a set of elements and you multiply them together, two at a time you get more elements, it forms a group, it has got the possibility of forming a group. But here the order of multiplication is important, it is a semi-group, it does not happen the other way, and so on. Okay. And I emphasize this because even when the Hamiltonian is time dependent, this would still happen. By the way, just 1 minute, let me point out in a second what would happen if the Hamiltonian is time dependent. Well, that is a much harder problem. If this guy were h of t, psi of t, then the solution is highly non-trivial, you can't do this. Look at it classically, you have d over dx, d over dt, some f of t equal to h of t, f of t. Suppose f of t is just an ordinary C number function and you have an equation of this kind. If h were a constant, then you would write e to the power ht and that is the end of the story. But what is the solution now? F of 0 given, initial condition is given. What is the solution to this equation? What is the solution to this differential equation? F of t equal to e to the power integral 0 to t dt prime h of t prime f of 0. That is the solution. Of course, if h is time independent, this integral just becomes t, but otherwise this is the solution to this differential equation. You can see immediately this is much more complicated than the original thing, which was just a simple exponential in time. This could be a very complicated function of time. How do you verify that this is the solution? You differentiate, then you have to find the derivative of this quantity as a function of t, and you use this famous formula for differentiation under the integral sign. I presume everybody knows that? Yes? Yes? Does anyone not know it? Everybody knows it? How to differentiate under the integral sign? Yes? We will see. Okay. So this here is the solution for this problem here, but it is not the solution for this problem here, and the reason is there is no guarantee, this is a summation. So it is like writing e to the power h at one instant, next instant, next instant, adding them all up. There is no guarantee because of this property e to the a, e to the b is not e to the a plus b. There is no guarantee that this is a solution because h at one instant of time may not commute with itself at another instant of time. Then you immediately run into a problem. So this is not the formal solution, it is not somewhat complicated, much more complicated, and when we look at time dependent Hamiltonians I will point that out. But the evolution still is unitary, it still is true that you can write psi of t as u of t comma t0 psi of t0 with this being a unitary operator with the semi-group property. It is still true, but it is a much more complicated formula. It is called a time ordered exponential, and we will look at that a little later. So the formal solution to the Schrodinger equation looks fairly simple, but it is not all that simple because it involves exponentiation of the Hamiltonian, and this is always a non-trivial task. You have to take a matrix and exponentiate it. You could in principle do this, but if you take a differential operator and exponentiate it, it becomes much more complicated. So that is the basic problem in quantum physics, that you need to find the exponential of the Hamiltonian. But there is nothing new, because even in classical statistical physics, on any statistical physics, you have to find e to the power minus beta h. So exponentiation of the Hamiltonian is in fact the fundamental problem both in statistical physics, equilibrium statistical physics, as well as in quantum mechanics, and it continues to be the case in quantum field theory. This is the reason for the commonality of all these subjects, the mathematical commonality, that you need to exponentiate the Hamiltonian here. What I will do next time, that is tomorrow, is to start with this equation here and show you why the Hamiltonian plays such a fundamental role. It is called the time infinitesimal generator of time translations, and we will see why it is so fundamental. It is analogous to what it does in classical physics, but in quantum physics you can see it plays an even more fundamental role because it really controls the entire state of the system, as you can see, and we will see why here. We still, having done this, we still have to make contact with the classical Hamilton equations. What are they going to be replaced by? We replaced it by the Schrodinger equation, but I would like to show that for physical observables there exist differential equations called the Heisenberg equations of motion. They replace, they are the true analogues of the Hamilton equations of motion. We will derive it backwards from the expectation values. Okay, so we will do that tomorrow.